Good morning, good afternoon, good evening, or good night. I'm not sure when you're watching this, but here we go. This is the second lecture on chemistry. First one was inorganic chemistry. Remember the atoms and periodic chart, protons, neutrons, electrons, valence, bonding capacity, all that stuff I taught you. Got it? That was the first one. And it was in your module under inorganic chemistry or chem review. Okay. This one is going to be under organic chemistry, biochemistry. So it's in the next module. This one's going to be a little long. As you can see from the side over here, it starts with slide 18 and it goes to slide 44. And some of it's going to get a little tricky. I will do my best to make sure it's understandable. Okay. If not, get a hold of me, get a hold of Sarah, or specifically get a hold of Brooke and get in the SI session. So what I'm going to do is I'm going to go to, I know what I got to do. I got to move this down to the bottom. Go to slideshow. I'm going to make it bigger for you. That's what I'm doing right now. Come on. Current slide. That's not what I wanted to do. Let me go back. I want to get to slide 18. I could go back through the others, give you a review, but you have them. Let's get moving. All right, current slide. There we go. All right, let me move myself up here to the corner. Okay, organic biochemistry. Remember we talked about this, organic living things. It also branches out into biochemistry, which is bio means living, the living chemistry in the body. So it's a toss-up. I don't want you to get organic confused when you go into the grocery store and you're looking at vegetables and it says organic, or you look at meat or whatever it might be and they say this is organically grown. Organic means it's living, man, okay? Or it was living. So scientifically, it's a little different than what you see in the grocery store. Okay, with that, we're gonna get started. Boy, that was thrilling. What's the matter here? There we go. It says organic or biochemistry, molecules that contain carbon, hydrogen, oxygen, and many times nitrogen, sulfur, and phosphorus. Watch this, CHON. C-H-O-N. Look at the first four. C-H-O-N. Okay? C-H-O-N. Those atoms, remember those atoms we were talking about? Elements? C-H-O-N. Carbon, hydrogen, oxygen, and nitrogen make up 96% of all living things. That means if you took and melted yourself down, 96% of it was going to be those atoms. Okay, you say, well, I thought most of what I was made out of water. Water is a compound, okay? Hydrogen, oxygen, got it? So you take the water, break it down further, and you have hydrogen and oxygen. You see where I'm going with this? You add in sulfur and phosphorus, the last two, and you're at 98.6. Remember that? 98.6. You melted yourself down, you throw in the other 2.5%, and you've got nitrogen and, sulfur and phosphorus. And the way I used to have these little in lab, I still do. I have these little, they're kind of like donuts, and I think they're Hispanic. I'm not positive, but they're like a marshmallow, and it's a circle about this big, and it says on the outside sponge, S-P-O-N-C-H. Way to remember it, S-P-O-N-C-H. Okay? What I'm trying to do is give you some way to remember those six. Okay? Okay? All right, let's move on. This is the chemistry of living organisms. Organic chemistry, biochemistry is the chemistry in living organisms. Now we are dead in the middle of physiology right now. When you talk about anatomy, you're talking about the heart, the lungs, the larynx, the eyeballs, stuff like that. When you talk about how they work or how they function, now we're talking about physiology. In order to understand physiology, it's pretty much chemistry. Now, I don't want you to start freaking out on me thinking, oh man, I did terrible in chemistry. We're not going to be able to get this right. Yet. That's why they put me here, is so I can teach it to you. Okay. Ain't my first rodeo, so I think I can get through this. All right, there we go. It's the chemistry of living organisms. Now, when we talk about the chemistry of living organisms, we talk about 4 macromolecules. I told you this in the last lecture. There are only 4 macromolecules. There's not 5. Okay. 2 of these I know you heard of, maybe even 3 of them. 4th one, I'm gonna have to teach that one to you. The 4 macromolecules, carbohydrates, proteins. Okay, you're on those too, right? Next one is lipids. That's the same thing as fats. We don't want to say fats, that might hurt somebody's feeling. So we say lipids. Okay, there's 3. There's 3. And the last one is nucleic acids. You say, I heard of nucleic acids. Good. DNA. Guess what the Na stands for? Nucleic acid. The first part stands for deoxyribo. Okay, so that I'm going to explain those to you. Remember us talking about pearl necklaces? Remember that? Okay, the pearl necklace carbohydrate, the pearl necklace protein, the pearl necklace nucleic acid. You get where I'm going? The nucleic acid, the pearl necklace lipids. Okay, now what is a pearl necklace made out of? It's not a hard question. Pearls. So in proteins, the pearls are amino acids. In carbohydrates, the pearls are monosaccharides. In nucleic acids, the pearls are nucleotides. Got it? Nucleotides. Got it? Fats, little bit different. The pearl necklace is a little bit scrambled, but it's fatty acids and glycerol. I'm going to explain this all to you. You understand the 4 macromolecules. Macromolecules in you, me, and all living things, period. Got it? You think it's going to be a test question? Probably something like, which is not a macromolecule? Got it? All right. Carbohydrates. Now, you also noticed it in my lectures, in my PowerPoints, I use colors because I think colors catches your attention to things that are important, like the very top, organic biochemistry. Well, that's the topic, okay? Black says, when I use black, I'm trying to say, this is going to define it, or this is a characteristic of it. When it's something important, I'll change the color to green or sometimes purple, that kind of stuff. So it says, this is the chemistry of living organisms, yeah? And then 4 macromolecules. Okay, so I went back to red, there's 4. Now I'm listing them: carbohydrates, lipids, nucleic acids. Let me get this guy out of the way. And proteins. Now you think, well, why did you list them that way? Because we're going to go through these. I'm going to tell you characteristics of them. I'm going to say, what is a pearl made out of? It's for the first one, it's a monosaccharide. Well, what is a monosaccharide? Like glucose and fructose and that kind of stuff. Oh, I get it. Lipids. What are lipids made out of? Glycerol and fatty acids. What's a fatty acid? You see where I'm going with it? So I save proteins for last, and here's why. When I do proteins leads us into protein synthesis. Got it? And that's a topic, remember, that's coming up. And nucleic acids, I talk a little bit about DNA and DNA replication. So the first 2 are pretty much straightforward, okay? Now, there's going to be a lot of stuff for you to write. So if you feel that I'm going a little too quick, just pause it. You have a pause button there. Pause it, back up, go through it again. Make sure your notes are accurate, because I guarantee you I'm going to ask you stuff that I'm showing you right now. That's what's going to be on your exam. Got it? Don't just look at this stuff and say, oh, I've got all this stuff about organic and biochem. I'll just memorize that slide. You memorize that slide, you're going to fail my course. Okay, because listen, you notice how I bullet everything in? That didn't work. That didn't work. Anyway, you notice how I bullet in one, then we talk about it. Then I bullet in the second one and we talk about it. And then I bullet this in and we talk about it. Look, we've been on one slide and I've been talking for 10 minutes. Okay, that's what you want to add to this. And I also would like you to do one other thing. When I'm asking you questions, pause it and guess. Because I tell you what, if you don't wait for the answer and you're guessing, that means your brain's engaged. And the chances of when you find out the right answer, you'll remember it a lot easier than just going, hey, I wonder if you're going to ask it on an exam. Okay? But one thing that really irritates an instructor and also really irritates Brooke is he goes, what's going to be on the exam? We usually come back and say, not a darn thing. We're just going to go ahead and have pizza and beer. Okay? So you know what's going to be on exam? This. Okay, let's move on. Macromolecules. Okay, what are the macromolecules? We just went over them. How many of them are there? 4. Is that true of all living organisms? Yes. What are those? How did we equate what a macromolecule was? Pearl necklace. That gives you the visual that a pearl necklace is a whole thing. You put it around your neck, you got a necklace. But if we go look at it closer, we know the pearl necklace is made out of pearls. And the pearls are going to be in proteins, for an example. There's 20 amino acids. In all the living world out there, there's 20 amino acids. And depending on how many of them you put in order and what order you put them in, you get a different protein. You get it? Okay? All right. Except lipids, all the macromolecules are made of repeating monomers. Now, don't let that freak you out. You got to learn the language. No matter what topic, whether we're talking about the heart, respiration, or we're talking about chemistry, there's a language that goes with it, and you got to learn the language. It's just a way of communicating, and that's what I'm going to ask you on exam. How did we communicate this? Monomer is like saying car. Okay? Hey, there's a car out there just went by. Oh, wow. Can you narrow it down for me? Can you tell me a color, a make, and maybe a sub-make? Oh, a Chevy. Do you know how many Chevys are out there? Okay, so when we say monomer, it equates to a car. Okay, well, what are monomers? What kinds of monomers? Well, there's monosaccharides. There is amino acids. There's nucleotides. You get where I'm going? So a monomer is just a generalized term that means any pearl. Are we getting it? Monomers are the single essential compounds. Now you remember, for an example, in carbohydrates, the monomer is a monosaccharide. Got it? The most common monosaccharide in living organisms is glucose. So if you look at that, glucose is C6H12O6. That's a molecular formula. Remember that? So C6H12O6 is a compound. So that's why it says monomers. Let me find my arrow. Monomers are the single essential compound that make up a polymer. You go, oh man, here's another word. Yeah, poly, many, mirrors, pearls. Got it? One pearl, many pearls. Example, amino acids are monomers. These are examples. Don't worry about polymer right now. Monomers, amino acid, monosaccharide, and a nucleotide are examples of monomers. That's the pearl necklace. Are there different types of pearl necklaces? Yes, there are. Do those pearl necklaces fall into 4 categories? Absolutely. But are there different subcategories? So in other words, if we have are there different types of carbohydrates? A carbohydrate is a pearl necklace. Are there different types of carbohydrates? Hell yes. Okay. Are there different types of proteins? Oh, hell yes. You get it? So polymers are numerous monomers bonded together that eventually form the macromolecule. Are you going, oh man, now we have another word, macromolecule. Well, wait a minute. That's the topic we're talking about. Macro, large molecules. Okay. There are 4 large molecules: proteins, carbohydrates, lipids, and nucleic acids. Proteins, carbohydrates, like cellulose and glycogen. Okay, I went on to give you a little more example here. Proteins, you pretty well got figured out. Carbohydrates, you say, yeah, I know what those are. Those are things you're not supposed to eat, can make you fat. No, no, no. Okay, cellulose. Cellulose is what makes the cell wall, not plasma membrane, not cell membrane. Cell wall is made out of cellulose. So every plant cell has an extra cover around the outside called cellulose. Got it? Glycogen is the form, oh wait, getting back to cellulose. It's made out of glucose molecules hooked together. So your whole pearl necklace is made out of nothing but glucose. Got it? Got it? Until it's functional, and then it's called cellulose. Okay, now glycogen is the way animals store glucose. So I give you glucose, I give you another glucose, I'm giving you pearls until you make up, you attach them together, and then you store them inside your fat cells, and skeletal muscle and liver. Well, how do you store glucose? We store it as glycogen. We cannot store it as cellulose. You understand? Okay, now we're going to do molecular formula. Molecular formula. Remember I said the molecular formula is how many atoms of that thing we have, like carbon dioxide, CO2. Hang on just a minute. Okay, we were talking about organic chemistry, and before I can get into the different makeup of carbohydrates, the different makeup of proteins and that kind of stuff, I've got to talk about molecular formulas and structural formulas. Now, I talked to you about this before, okay? Molecular formula is what you see here. How many of each atom do you have, okay? Structural formula is what it looks like if we put bonding on it. And I showed you that, okay? I'm going to have a lab on this. It's called Atoms and Molecules, where I'll introduce it to you, and then you'll do that lab and you'll turn it in for points, okay? And it just has you working with going from molecular formula to structural formula, from structural formula to molecular formula. So you understand it, okay? So when somebody throws up C6H12O6, you're going, oh, that's a molecular formula for glucose or fructose. Yeah, you see what I mean? Okay, okay. That being said, let's go to the next one, structural formula. This is what the molecule looks like, okay? Showing the atoms and the bonding, okay? It's a picture of the molecular formula. So first one, get out of here. See that's CO2, CO2. And then you see there's carbon has to have 4. Remember we were talking about valence and bonding capacity? Bonding capacity of carbon is 4. 1, 2, 3, 4. And the bonding capacity of oxygen is 2. 1, 2, 1, 2. You see. So that's done properly. Okay. I have another one with C6H12O6. Okay. An isomer. Now we talked about this when I did the outline. An isomer is a compound or a molecule that has the same molecular formula but different structural formula. So in other words, here's an example. C6H12O6. That's glucose. Everybody tells you that. But it's also fructose. Fructose is C6H12O6 also. Well, why do they have a different name? Because they have a different structural formula. Okay, C6 glucose is looks, and I'll show you what it looks like. Glucose looks like a structural formula looks like one way, and fructose looks another way. So well, what happens? You get 2 different things. If they're structurally bent, twisted, or manipulated in some way, you got something different. Okay, you take your pearl necklace and you twist it a certain way, you got a different looking pearl necklace. Yeah, even though there's 6 carbons, 12 hydrogen, and 6 oxygen. Do you see where I'm going with this? Okay. An isomer. It has a compound or molecule that has the same molecular formula but different structural formula. Example, glucose, fructose, which I just told you, and galactose are all C6H12O6. Okay? Now, the one we always talk about is glucose. Glucose, but it's not the only fish in the pond. Got it? So an isomer, I'm going to ask you on an exam. It is a compound with the same molecular formula, but different structural formula. Are we good? Okay, now here's the structural formula. See this? Molecular. See this? Molecular. See this? Excuse me. Structural formula. Now, here's glucose, here's galactose, and here's fructose. Immediately, you can see this is a pentose structure, and this is a hexose structure. I mean, six-sided, okay? And you can see that the difference between galactose and glucose, you just switch this guy right here. This one goes up, H goes down, and galactose. You're saying, well, it's going to be the same stuff. No, it's not. Okay, those are isomers of one another. Now this, you see the molecular formula? They're still the same. And then down here, 1, 2, 3, 4, 5, 6. Still has 6 carbons. Got it? Got it? Okay. You understand what an isomer is? And anything to do with an isotope. Isotope means it has more neutrons. Remember that? This is an isomer. All right. We got them all over our body. That's straight biochem. Okay, metabolism. Remember we were talking about metabolism? I says, hey, if I had you define metabolism, what would you say? Pause this. Okay, now you came back to me. You would have said, oh, that's when you break stuff down. You are absolutely almost right. There's 2 types of metabolism. Breaking it down, which is called catabolism, and building it up, which is called anabolism. I didn't know about anabolism. Yeah, you did. Anabolic steroids. Yeah. Don't get hooked into that. Don't do that. Don't do that. Because it triggers growth of muscle. Yes, it does. You'll look like Hulk Hogan, man. I kind of look like Hulk Hogan, huh? Anyway, you'll look like Hulk Hogan. The only problem is it doesn't differentiate what muscle, and we have 3 different types of muscle: smooth, cardiac, and skeletal. When it's skeletal, you're going, oh man, look at me, you know. Yeah, but what about if it makes your heart grow and tries growing outside your chest cavity and you die? My son had somebody like that. Okay, he looked like a muscle bound. He was muscle bound, man, and his heart. He didn't realize he couldn't see it. His heart started to grow inside of his chest until it put out so much pressure. He's gone. Yeah, and he is gone. Okay. So don't do that. Don't do it. Okay? And catabolism, to break down. So when we eat those pearl necklaces, we have to break it down into the pearls. The process of taking the pearl necklace and breaking it down into the individual pearls is called catabolism. It's also called hydrolysis. Remember when I did this? We did this in inorganic chemistry? Yes? When you build something up, that's called anabolism. So you take the pearls and you're a jeweler and you're starting to make a pearl necklace. You're going through anabolism. Yeah. And we also know that as reduction. Remember I said, because reduction sounds like you're making it smaller. Synthesis, condensation. Remember those terms? Okay. Keep that in mind. So now you know what it applies to macromolecules also. Catabolism means you take a large compound such as a protein and break it down into amino acids. Okay, now in the body, now we're starting to get into the human body as well as other living things. In the body, it takes an enzyme and water to make catabolism. So you have to have a specific enzyme. You're saying, well, why can't you just have a generalized enzyme? Because then you don't have any control. You need one enzyme that breaks down one compound, period. That way you have total control, because to make an enzyme is a protein. We go back into our genetic code in protein synthesis, which I'm going to show you later, discuss later, and you make this protein. Got it? That means you can control your catabolism and anabolism, because this applies to both. okay? And you got to add water. When you break it, you got to add water. Other scientific terms, oxidation, catabolism. We already did this, we'll do it again. Catabolism, oxidation, not reduction. Oxidation, hydrolysis, okay? In lab, I'll just see if this works. Because some people didn't know that. They had hydraulic mining. You know what that was? When they were back in the gold rush and they were trying to get gold, and they knew it was in the mountains. So what they did is they went by a stream and they got a big thing that looked like a fire hose, and it shot water onto the water and shot it onto the mountain, and eroded the mountain away, just like our rainstorms do, okay? And it broke that mountain down into smaller pieces. Catabolism, hydrolysis, get it? Okay. Anabolism means to make a small compound like a monomer, remember what that is, and bond it with other compounds to make the larger ones, like a polymer. Remember those monomer, polymer, just common name, okay? Good. And it removes water. Okay, that's why we hear the word reduction. Got it? Condensation. Okay, synthesis. All right. Other scientific terms: reduction, dehydration. Water's coming off. Look, move water. Moves water. When you remove water in your body, you know you're dehydrated, right? Dehydration. Synthesis, condensation. Bunch of words for that anabolism thing, huh? And what happens in your body is you take in a pearl necklace, either by chewing, which is called mechanical, or chemical using enzyme. We break it down into pearls. Once it's in a pearl, goes in the blood. Blood takes it to a cell that needs it, drops it off, and then using your genetic code, you build it back up the way you're supposed to for your body. Yeah. I'm supposed to turn this. Okay. Anabolism versus catabolism. Now, what I'm doing now is I'm just giving you a structural, not even a true structural formula, but just a picture of something. And we call it a monomer. Got it? Now, dehydration synthesis means we're going to put that one together with this one. We're going to put a plus in here. We pull off water. See the water? We pull off an OH and an H, get H2O. That one oxygen stays, and that's what connects it. O, and then to another one. So we have gone from a monosaccharide to a disaccharide, like sucrose and stuff. You guys can't see my mug, can you? Let me turn it the other way. Let me see if I can do it this way. I got stuff all. As long as I don't think that. No. Let me take this thing out. Bear with me. There we go. You know, I used to define a geek by somebody that had more than one computer. I'm sitting here surrounded by 3 of them. Okay, that didn't go good either, did it? You can't see my mug. Turn it again. There you go. There I am. Kind of like kick back here. There we go. This is called a man cave. I got all kinds of stuff in here. See it? All kinds of stuff. Yep. Anyway, okay, now you've seen enough. Now when you get on a Zoom meeting or something like that, you always look around, see what the hell they got in the background. Okay, their house messy, you know. Yeah, I do the same thing. Okay, all right. All right. Here we go. So we were talking about dehydration, taking a monomer, a pearl, and attaching it to another pearl, which is called dehydration synthesis, reduction. It looks like they're not being reduced. Okay, that's just because you're pulling off water. And then you end up with this. Don't worry about a dimer or a dimmer. What this is a disaccharide, or a di. I guess it's a dimmer. Uh-oh. What the hell happened? Okay, I got to go back. Oh, I know how to do it. Previous. Okay, do you understand that? Okay, and here's hydrolysis. Remember, taking something big, remember the mountain? Taking it, squirting it with water and making it smaller. So hydrolysis, you take this dye, you add water to it, and there's what they're not showing you. You also have to have an enzyme, okay? And then you get your monomers back again. So just a minute. This and this, they're the same thing as this and this. This is this. So we build them up, anabolic, tear them down, catabolic. Pretty good, huh? Okay. Carbohydrates, general formula. Okay, I'm going to ask you this on the lab. I don't remember if I asked you on the lecture. Okay, probably because I haven't finished the lecture yet. All right, those things are a pain to do. I know. Let's all get together and let's not do them. Yeah, wrong. All right, general formula. CH2O. N means any number. Okay, so if this number is 6, I'll show you how this works. If this number is 6, we have C6, 2 times 6 is 12, H12, O6, glucose. You see? So this is general formula. It means there's 2 more hydrogens there is carbon and oxygen in a molecule. This N could be 100. Could be C100, H200, O100. Okay, generalized formula. You with me? Okay. I'm going to ask you this. A generalized monomer, monosaccharide. The most common monosaccharides, I already showed you what they look like, is glucose, fructose, galactose. Got it? No, I'm going to ask you that on an exam. I'm also going to ask you it in the lab. Disaccharides. Remember, you take 2 pearls, put them together, okay? Remove water, they go together. They're called a disaccharide. Here's the common disaccharide. Lactose. Remember, for those of you who are lactose intolerant, it's milk sugar. Okay, milk sugar. Maltose is another disaccharide, and sucrose, which you know what that is, it's called table sugar. You know why it's called table sugar? This is not a brain twister. It's called table sugar because you find it on a table. Okay, that's the one you put in your coffee and you put on your cereal or whatever you are, right? I just put a spoon. Okay, maltose is malt sugar. And I always take a second just to try and bring in reality. I know you sometimes you're just going, can you get to the point? Well, maybe. This makes it more interesting. Do you know the difference between a milkshake and a malt? You're going, what is a malt? I'm about to tell you. You ever hear of back in the old days, ask your parents about a malt shop? That's where they made malts. You can go in and get a milkshake, or you could get a malt. Okay. Okay. What's the difference? The sugar. Okay. If they put in sucrose, let's just make it easier. They put in glucose and they put ice cream in it, flavoring or whatever it is, and they stir it all up. You got a milkshake. Instead of sucrose or glucose, they put in maltose. Okay, just different sugar. It tastes different. And it was called a malt. You know the little Whoppers, malt balls? Yeah, you can get Whoppers. Okay, malt balls. Guess what the difference is? It's the sugar that they made the malt, the blue ball out of, is made out of maltose instead of sucrose. Okay, I hope you're going, wow, this stuff is really cool. And you're running out of your room to tell your family members or other people, man, I'm learning so much stuff. If that's the case, you're putting a smile on my face. Okay, polysaccharides. Okay, these are numerous monosaccharides. That's all. Poly just means a lot of saccharides. So a lot of pearls together is a polysaccharide. When they're bonded together and when they become functional. Okay, if you just start putting pearls on and you don't put the latch at the end, do you have a pearl necklace? I'll help you out. The answer is no. Okay, but once you put the latch on it, you've completed it, and now it's functional. It is called a carbohydrate. Okay, so functional, this is a test question. Functional carbohydrates or functional polysaccharides, sorry about that. Functional polysaccharides are called carbohydrates. The most common carbohydrates, we already went over this, cellulose. And what did we say about cellulose? Pause your computer and I want you to think. You're saying, but I don't want to think. Go back in your notes. You wrote it down probably 2 pages ago. Okay. Cellulose is stored glucose that also makes up the cell wall in plants. We don't have a cell wall. Animals do not have a cell wall. The other way plants store glucose in 2 ways. One in cellulose, the other one starch. Okay, so this is where I always use the example when we're face to face. I said, you have a potato or rice, okay, full of starch, right? That potato did not make the starch for you. Oh, come on, don't be so conceited. The starch the plant made was for it. So when the sun wasn't shining, it had glucose that it could turn into ATP. But we know that because we got bigger brains and we went out and we pop up the potato, cut the plant off and say, hey, see you later, man. And you got the potato full of starch that potato made for itself and you ripped it. Okay. So that's what starch is. So when we have very starchy stuff like rice and that kind of stuff, that plant is making it for itself and we rip it. Got it? And glycogen is animal. Sometimes they call it animal starch. And what we do is we take and we have to eat something else that's made it. So we eat glucose. If we eat it in starch or we eat it in cellulose, we have to break it down. Once it's broken down, we can use the glucose. Then we have too much glucose in our blood. Diabetic, for example, you have too much glucose in your blood. You got to take it out and put it in a cell to store it for when you need it. First place it's going to go is the liver, skeletal muscle, and finally into lipids. Okay. Now, hear me out. When we store glucose, we meaning animals store glucose, we store it as glycogen. We never store it as starch or cellulose. Sometimes I've heard people say animal starch. It's using the term loosely. There is no starch in animals. It's glycogen. You understand? All right. Okay. Now, remember the structural formula? This is a structural formula. This is a structural formula. Okay, I don't have the molecular formula. But here we have a pearl, monosaccharide. Here's another pearl, a monosaccharide. This one happens to be galactose. This one is fructose. If we put these together, remember, oh no, this is different. What they're showing you is they're different types here. This is a 6 carbon, and here's a 5 carbon. A 5 carbon sugar, ribose, and deoxyribose. Okay, just forget what the other stuff I just said. This is just showing them structural formula of a 6 and a 5 sided saccharide. This is showing you where you find 5 carbon sugars. Remember, because it was C6H12O6. You know this one's going to be C5H10O5. Remember, CH2O parenthesis N. In this case, the N is 5. Okay. Anyway, ribose is in RNA. The R of RNA is ribonucleic acid. In DNA, it's deoxyribo. Anyway, it's just examples where you use this. Okay, here's your disaccharides. This is what I wanted to do. So if you take This is, just let me get my arrow back. This is fructose, and this is glucose. If you take a pearl glucose and a pearl fructose, hook them together, you know, to do that, we had to pull off water. You get a disaccharide sucrose. So table sugar is a glucose and a fructose together, two pearls. Lactose, milk sugar, is glucose and galactose together. Okay, this is anabolic, anabolic reduction. No, anabolic, yeah, reduction, bringing it together and that kind of stuff. And maltose is two glucose molecules. You get it? So the common disaccharides that we have are in our bodies is sucrose, table sugar, lactose, milk sugar, and maltose, malt sugar. And they're made the same way. They're still a disaccharide, but they're made of different monosaccharides. Good? Glycogen, sometimes called animal starch. You see where I put that there? Okay. Okay, it's not accurate, but I hear it all the time. It's a storage form of glucose in animals. Do you think I'm going to ask that on an exam? Okay, if you're puzzled, the answer is yes. Glucose is a 6-carbon monomer that is metabolized into ATP. Cellular respiration is how we make energy. Us, humans, animals. Animals cannot make their own glucose. They have to eat something that has made it. And ultimately, what has made it is a plant. Okay, got it? Now, let's say you're a cow. You eat the plant to get the glucose to make energy. You also get proteins out of plants. You also get nucleic acids out of plants. And then you assemble them the way you want, and then we eat you. Get it? So it's everybody out there eating everybody, and they all ultimately are eating a producer, which is a plant. Something that's able to go through and produce its own glucose, which is just one of the things it does. Okay. Photosynthesis is production of glucose. You're also producing amino acids and all kinds of stuff in that plant. Okay, getting back to glycogen. If I'm giving you a lot of extra information, you think some of the stuff will be on the exam, most of it will be on the exam, some of it won't. Why am I giving it to you? Because it makes it interesting, makes you well-rounded. I don't want to just give you the facts and say, you just go memorize those facts and you'll be fine. I want you to understand why you're doing it. Okay, anyway, glycogen, animal starch. In plants, glucose is stored in two forms, cellulose and starch. Now, I've said this a bunch of times. You see it in a different color. You know you're going to see this on an exam. Glycogen is stored in the liver and skeletal muscle. I've already told you that. Okay. If you're thinking, oh, I didn't think that was important. It's okay. It's a learning curve. Yes, it's important because I told you where you find it. I said you go in the liver, skeletal muscle, and when those are full, where does it go? Lipids. Okay. When glucose is bonded, the process is called glycogenesis. Glycogenesis. Genesis is new glycogen. You're making glycogen. When it's hydrolyzed, broken down, it's called glycogenolysis. See that lysis? So this is anabolic. This is catabolic. You get it? You get it? Okay, it says the liver can make glucose from non-carbohydrate structures. That's called gluconeogenesis. Okay, whoops. Gluconeogenesis. I want to get back to that. Okay, so now look at what we learned. We learned what glycogen is. We know what glucose, fructose, galactose is. We know what cellulose is and starch. That's how plants store it. We know what glycogenesis is. All you got to know is the word genesis means new or to make. Glycogen, glyco. So when you take carbon and you add oxygen and hydrogen to it, you make glucose. That's called glycogenesis. Well, not really. It even goes further than that. Let me back up with that. If you take a glucose molecule and another glucose molecule and another glucose molecule you store it in animals, you store it as glycogen. That's where that comes from, glycogenesis, to make glycogen. When you break down glycogen, it's called glycogenolysis, to break, to lyse, to break. Okay, so how does that work? Well, we've always heard of insulin, haven't we? And we know that insulin takes glucose out of the blood. Okay, so insulin doesn't physically take it out. It opens up doors in certain cells that allows glucose to go inside. Once it's inside, there's an enzyme that puts it together to form glycogen, and the process is called glycogenesis. If you're a deficiency because you're running or you're working or something like that, and you need more glucose in your blood so you can get ATP, you have to break down that glycogen that's in the cell, and there's another enzyme that's released, and both of these are released from the pancreas, and it's called glycagon. Glycagon breaks down glucose and glycogen and releases glucose. It says the liver can make glucose from non-carb. When you make glucose using other things, which is more complicated, but it's according to your DNA, that's called gluconeogenesis. Now, those terms, watch. 1, 2, 3, 4, 5, 6. You're going to see those 6 on an exam. All right, that's it for carbohydrates. Pretty straightforward, huh? Okay, let's go to lipids. Now I jumped to lipids. In your book, it'll go carbohydrates, and then it goes to proteins. I want to say proteins because that to the end, because that leads us into protein synthesis. Okay, lipids. Lipids and fats are the same thing. When I went to school, they called them fats. I don't know. I always use the story that because some people that were very large got upset, they didn't want to be called, because they used to back then, they used to say fat people are happy. Okay, and then they didn't want to use fat people, so they said lipid happy. I'm making it up. Okay, if that hurt your feelings, I'm sorry. Just trying to make it up. Lipids. Okay, lipids, they are not polymers. Ooh. Polymer. Remember, a polymer is a necklace. Lipids don't work that way. They're actually 3 necklaces tied together. Okay, multi-string. You'll see what I mean. They're all characteristic of lipids. All lipids are hydrophobic, like water. So oil, pour oil on water, what happens? Floats on the surface. Therefore, it's hydrophobic. You take wax, put it on water, what happens? Floats right on the top, hydrophobic. You understand? If it is repelled by water, it is hydrophobic, it's a lipid. All lipids are hydrophobic. Got it? Okay, I said now lipids. Some lipids are hormones. In other words, you got a whole bunch of hormones out there. You know that, okay? Especially when you're like 12 years old. There's all kinds of hormones out there, okay? If you're parents and you got a kid that's 10, 11, 12, 13, and they're going through the hormonal changes, OMG, right? How this cute little kid that you love with all your heart turn into that little monster. Hey, it's hormonal, okay? And they'll get over it once they adjust, because they're going through a stage where the body is producing a lot of hormones to control growth and development. Does that make sense? We will talk about that, because there's 2 things that control body functions. One is the nervous system, and the other one is the endocrine system, hormones. Okay, now that being said, there's 2 major classes of hormones. Those that are protein-based, you'll find out it could be amino acid too, and those that are lipid-based. The lipid-based are the ones we always hear about, like testosterone, estrogen, progesterone. That means they start with a fat, and the fat is cholesterol, and then they add things to it. They add compounds to it, and depending on what the compound they add to it, you get a different hormone. So there's lipid-based hormones and protein-based hormones. Okay, so it says lipids. They form some hormones, major portion of the cell membrane. We find lipids in the cell membrane, and the body uses it as future energy source. Okay, Okay, got it? Or do we know that one? Man, I fight that all the time. They begin with cholesterol, and then compounds are added to it. Picture this. Cholesterol is it's got 3 attachment sites. Okay, it's a 3-carbon compound, and you can attach things to those. If you attach it here with a fatty acid, and you attach it here with a fatty acid, which is a long hydrocarbon chain, and you attach it here, okay, that is called a triglyceride. Glycerol. Okay, and you've heard of triglyceride. Stay away from triglycerides. They'll plug up your circulatory system. Because you have some triglycerides doesn't mean you're going to die. That isn't the. It just says if you're flooding your body with too much of them, yeah, it could be a side effect that ain't too good. Okay. Okay. Now getting back to that thing. Here's your glycerol molecule. Okay. So the palm of my hand is the glycerol molecule, and here's 3 attachment sites. If you attach those to those 3 attachment sites with a fatty acid on each one, you have a triglyceride. If you put a phosphate on one of them, still have 2 fatty acids, this is called a phospholipid. If you add a carbohydrate to it, you have a glycolipid. If you add a protein to it, you have a lipoprotein. We switched it. Lipoprotein. You see? So those 3 little places you can attach to, the more you attach to it, you just change the name of what it is. There's 4 classes of lipids. Triglycerides. Didn't we just say that? Phospholipids. Okay. Phospholipids. Steroids. And echino, or they pronounce it 2 ways, econo or iconosanoids. Econosanoids. What are those? Well, you're going to find out. They're a classification of lipids. Glycerol, 3-carbon molecule. Okay, and I said if you have 3 fatty acids off each one of the 3 carbons, a fatty acid called a triglyceride. Good. If there's 1 fatty acid is replaced with a phosphate, it's called a phospholipid. I'm making a big deal out of this phospholipid because our plasma membrane, the cell membrane, not the cell wall, the cell membrane is made out of phospholipid. Not the only thing it's made out of, but that's its major source. You understand? So it's this thing, take away this, put a phosphate on it, do it this way. Put a phosphate on it, and now you have a phospholipid. You understand? If one of the fatty acids is replaced with a protein, it's a lipoprotein. Just went through these for you. If the fatty acid is replaced with a carbohydrate, it's called a glycolipid. Okay. Now, you remember we said that there are 4 macromolecules, and what we're doing now is we're taking those 4 macromolecules, and I'll just do it this way. And we're plugging things on to the lipid, and we're getting different types of we're building up a bigger than a macromolecule. So we're taking the 4 classes of macromolecules, putting them together, and we're getting this much bigger chemical compound. That's what I'm trying to say. Okay, and depending on what that is, it has a different function. You know, how does the cell next to you know it's an eye cell? You're an eye cell, the cell next to you is an eye cell, and when you go through DNA replication, you make more eye cells. How does that happen? Well, what's embedded in the phospholipid bilayer, either a glycolipid or a lipoprotein or something like that, it tells you, hey, bud, we're eye cells. We can only make eye cells. Okay, if the fatty acid, okay, this is a good one. Have you heard of saturated fat and unsaturated fat? Okay, hang on a minute. Okay, if you have a fatty acid and it's single bonded, now what that means, you're going, what do you mean fatty acid single bond? Remember the glycerol? And you had fatty acid chains out there? The fatty acid chains are called hydrocarbons. Now don't freak out on me on the language. Remember I said You got to know the language. A hydrocarbon, a carbon with hydrogen attached to it. That's all it is. So when you have a whole string of carbons with hydrogen hanging on it, you have a fatty acid. That's all. And that's just the acid part is on the functional end. So you have carbon, hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, hydrogen for however you want, 100, 200 carbons out there. But right at the very end, you have a C carbon, double bond O, OH. That's a carboxylic acid. When you put that on there, it becomes a fatty acid. Hey, okay. Don't you wish you knew this when you're in chemistry? Okay. A saturated fat means it's saturated with single bonds between the carbons. And I'm going to show you a picture of this in a minute. So you have a carbon, single bond, carbon, single bonds, carbon, single bond. That's a saturated fat, and it's a solid. There's your test question. It is a solid. When it has one or more double bonds between the carbon, it's called unsaturated. If it has one, it's monounsaturated. If it has two, it's diunsaturated. If it has a buttload of them, it is called polyunsaturated. And I can remember when I was a kid, yes, I can remember back that far. When I was a kid, they used to, when they realized that saturated fats that we were using a lot to cook with, like lard is animal fat. It is absolutely, completely saturated carbons. And it means it's a solid. And with fat, we get flavor. So they cooked with fat all the time. They made French fries. They didn't cook it in vegetable oil or canola oil or olive oil. They cooked it in lard. And when lard is heated up, it turns into a liquid. Got it? So when you heat up the bacon, for an example, you got fat on bacon, right? Fat is a solid, isn't it? Because it's an animal fat. Hey, it came from a pig, man. When you heat it up, you put in double bonds. When you put in a double bond, it makes it a liquid. The more double bonds you have, the more liquid. So the theory was back then, they changed to oil. Oil is a fat, Jacko. It's just plant fat. Plant fat is a liquid. Do you understand? Okay, animal fat is a solid. Okay, now if you want to make animal fat a liquid, you heat it up and you put double bonds in it. The more double bonds you put in it, the more liquid it is. And you've done this with bacon fat. You heat that sucker way up, and man, that oil is just thin, huh? And then when it starts to cool, because you're losing those double bonds, it starts to thicken. Yeah, until it's solid again. Okay, so a saturated fat, test question. A saturated fat has single bonds in the carbon chain, period. If it has one double bond, here's your test question. If it has one double bond, it is no longer a saturated fat, it is an unsaturated fat. Okay, it says right here, if one fatty acid has one or more double bonds, it is considered unsaturated. You understand the difference between saturated, unsaturated? The bonds. One bond, saturated. Two bonds, unsaturated. The more unsaturated, the more of a liquid. Got it? Got it? All right. Here is a saturated. I got to teach you something about chemistry. This is the end. This is what makes it an acid. C double bond O. Dang it. Didn't want you to see that yet. The C double bond O is only part of it. As C double bond O, OH, and then an OH down here. Okay. So that makes it a carboxylic acid here with the hydrocarbon chain is what they call a fatty acid. Okay. R means it's like the N we saw in the molecular structure. R just means, hey, I got a whole bunch of them. So in organic chemistry, when we're writing we're writing the molecular formula, I mean the structural formula, we don't want to put a bunch of bonds out there. because we know if it's on a lipid that it's a watch here, a CH, H, CH, H. That is called a hydrocarbon. And that's all it is. It's just a string of them. And some fats might be 200-300 carbons long. So what you would do is you'd put C double bond O, and then this C right here would be an R with how many carbons there are. So you'd see this C double bond O, which is your functional group. And then this C right here would be an R. So you'd go C, R, 100, and 2. There'd be 102 of these guys out there. That's all it is. That's just a shortcut. Got it? Now look at this one. Same thing, only I threw a double bond in right here and right here. So this is an unsaturated fat. There's 2, it's a di. And I still put the R out there. Got it? Now, here we go. We're summarizing. Saturated, animal fat, solid, bacon. I gave examples of that. Memory candles. Okay, I want to go back. This is something that's kind of interesting. Okay, so animal fat is solid, like bacon. And I put lard. Okay, lard is just fat. And it used to be a good cooking tool. Like Crisco is animal fat. And they use it for flavor. Okay, plant oil, like corn oil and vegetable oil and stuff like that. I had to go buy some today, and I got vegetable oil, and they had corn oil and they had safflower oil, just all plant, and they squeeze the lipids out, and it's an oil because it's unsaturated. You see, saturated, lard, bacon. I just gave you an example of that. And I had memory candles. What the hell is a memory candle? Okay. If you took, you know how they used to make candles? They took an animal that they were going to eat. They would scrape the fat out. They would make a casting, a tube, and they'd put a string in the middle of it. And they would take and heat up the fat into a liquid. They would put double bonds into it, making it a liquid. They'd pour it into the form. They'd let it cool down. When it cooled down, it lost the double bonds, became saturated and a solid. They took the form away and they had themselves a candle. And the candle, when you heated it up, it burnt the string heated up the fat would melt, they'd catch it. After the candle was done, they'd take another piece of string, heat up the fat again and start all over, okay? It was the beginning of recycling. Got it? All right, memory candles. You can take any animal, scrape the fat out, heat it up, turn it into a candle. Unsaturated, plant fat, oil, cooking oil. We good? Okay, now, don't freak out on me. You see this? This is glycerol. See, 1, 2, 3 carbons. Do you see that? And you take an H off of this one and an OH off the, remember I said this is a carboxylic acid, C double bond OOH. So you take off the OH and you take off the H and you get water. Because what we're doing here is this is anabolic. This is condensation. This is reduction. Now, so then this is going to be a fatty acid. And we're going to have a C double bond O and O, and then to the glycerol molecule. This is a hydrocarbon. And guess what? What kind of a carbon? You see that double bond? So this is unsaturated, isn't it? This one is saturated. You see there's no double bonds. See it? This is a hydrocarbon chain. So instead of drawing all this out, you'd go, oh my God, I got to draw 102 carbons with H's on them. No, right here, this would be an R, and it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It would be R18. That's how we would shorten it. Got it? So this is a triglyceride, and there are two fatty acids on it that are unsaturated and one saturated. You see how you read that? Son of a gun. And then what they did here is they're pulling off water to attach this fatty acid to a glycerol molecule, making this a triglyceride. You see? Wow. Okay, now I want to take you and pause you for a minute. What I want you to do is realize you're taking notes. You're not just looking at the pictures. Stop me. I don't care if you got to stop me 100 times and write it and go back and listen to it again. So to go through this lecture is going to be about 2.5 hours long. Okay, you stop it, go back to it. Okay, if you do this right, a 2.5 hour lecture should take you about mosquito. That 2.5 hour lecture should probably take you about 6 hours. Okay, because you're learning, you're refining your notes. Okay, so you're not just looking at this stuff, you're understanding it. All right. Adipose tissue can be formed anabolic or broken down catabolic. Okay, now we all struggle with adipose tissue. I just should say that many of us do, yours truly included. And that means you're always fighting it, okay? So if you saying, well, I'm not gonna eat lipids, I'm just gonna eat carbohydrates. Okay, yes, surprise, when you step on that scale, it's all of a sudden those carbohydrates are lipids, because what your body does is you can only have a certain percentage of glucose in your blood. Got it? If you have too much, you release insulin from the pancreas, it opens up doors and it tells the glucose to go into liver or a skeletal muscle until they're completely full. And then insulin's looking, it's going, oh my God, where am I going to put all this glucose? Because they just had 4 potatoes and a bowl of rice. It says, wait a minute, we're going to go, we have a specialized cell for storage of that. And it stores, those cells are called adipocytes, and they store glucose in the form of lipids. Do you understand? And so when you break it down, here's what you get. You're going, oh man, January 1st. Oh, I'm going to lose 10 pounds. So that's your New Year's resolution, right? You can't lose. The gyms are still closed, but it doesn't mean you can't go in your house or run around your house or your apartment or your yard or whatever it might be. The first thing you will exhaust. So you're going out there and you're running, all of a sudden you're going, oh man, I'm tired. What you have exhausted is glucose in your blood. Your blood level of glucose went down. So what that did is it triggered a glycagon to be released from the pancreas, and it opened up doors in cells in the liver that break down break down glycogen into glucose and dump it in the blood. Then you get your second wind. You're going, hey man, this is pretty good. Okay. And it also breaks it down in skeletal muscle, about the same. Okay. And you're going along pretty good. You're going, hey man, I got my second wind. I think I can go forever. And all of a sudden, it feels like you hit a wall. Oh my gosh, I can't hardly move. And then what you tell your body to do is to go to the last source. Last in, last off. And that means it gets to the adipocytes, those storage cells, the fat cells, and it starts saying, hey, come to me, buddy. We're going into the blood. So then it releases glucose into the blood, and you get your third wind. Most of us don't get that far. After we're done with the second wind, we say, okay, I'm done. Okay. Then we go out and have a bunch of carbohydrates thinking, man, I worked out and now I can afford to. No, all you're going to do is fill back up the skeletal muscle and the liver, and you'll be right back to where you were before. You got to get to that third wind, which takes most people about 20 minutes. Okay, I'm going. Adipose tissue. Lipogenesis. Remember, genesis to make. Lipids. I just told you about it. Okay. You get too much, you're going to start storing it in places you want it to be stored. Lipolysis. Now, this you do want. You say, okay, I'm going to trim off 5 pounds, 10 pounds, something like that. I've got to get to my adipocytes, my fat. That's where I want to lose it. I don't want to lose it in muscle. I don't want to lose it in my liver, but I got to lose it out of my muscle and my liver first before I get to the the fat. The other thing you can do is you lose it from the liver, you lose it from the skeletal muscle, and then you don't replenish it. No more glucose. And then your body's going, hey, the liver says, hey, ship me some glucose. Skeletal muscle says, ship me some glucose. So it pulls it out. Got it? Okay. My problem was, as soon as I got done working out, I didn't have any glucose in my liver or my skeletal muscles. And then I went out and had a big milkshake. Okay. Woof. Not too smart, buddy. Okay. Okay. Phospholipids. One of the fatty acids, hydrocarbon chains, have been replaced. Remember I did this? Said you had 3 and you take one away and you put a phosphate group on there. Phosphate is just an element. Now you have a phospholipid. Look what I said. It's a hydrocarbon chains have been replaced by a phosphate molecule. Major component of a cell membrane, phosphate. And it's hydrophilic. Okay. Phosphate is hydrophilic. Fatty acid is hydrophobic. You're going, I don't get it. Well, if this is the phosphate and you point it towards water, water can lay right against it. And your body is made up of a lot of water, so you have to be hydrophilic. So what it does is the phosphate groups here, the fatty acids here, put the fatty acid away from the exteriors, exterior, interior. So you point it towards the inside. So our phospholipid is a bilipid. There's 2 of them, one on the top, one on the outside, one on the inside, with the fatty acids pointing towards the middle. Get it? So that means our cell can have liquid inside, liquid outside, no problem. It's trying to get through that cell membrane that's going to be a problem because it's hydrophobic. Steroids. Steroids are lipid or protein based. Lipid begins with cholesterol like testosterone, estrogen, bile. Got it? Eicosanoids are just a little bit different twist. They're a finite amount of fatty acid chains, 20 of them, 20 fatty acid chains. Okay. Remember we have 3. Okay. 20 acids. The carbon chain is 20. You don't have 20 fatty acids. It's just your R, remember your R is only 20. And they're signaling molecules. This means they signal immune responses, inflammation, cell recognition. Remember I talked about eye cells? Guess what? It's hanging out there in that phospholipid bilayer. Okay. Eicosanoids. Got it? They also were learning about the COVID, you want immune responses. So those are the things that are out there signaling what they are. Okay, let's take a look at this. Okay, do you see the C double bond O? That's a carboxylic acid. So we call this a fatty acid. Fatty acid. This one's saturated. This one's saturated. This one's saturated. Example of a triglyceride. Got it? Now, if you take one of these off, take one of these off, this one doesn't matter, and you put a phosphate on there. You see it? There's your fatty acid. That one happens to be unsaturated. Here's your fatty acid, and then here's your phosphate. This is a phospholipid. Plasma membrane. I'm going to ask you on an exam. Miscellaneous lipids, ketones. Okay, you've gone into the doctor's office and says, oh man, you're passing ketones. And don't be depressed. Ketone is the breakdown of fats, man, fatty acid. Now, it's also an indicator if you're a diabetic, you'll start buzzing off ketones, throwing ketones in your urine, okay? So in the presence of urine, it's a breakdown, lipolysis of fat, ketones. Surfactants. Okay, let me explain what a surfactant is, because we're going to see it in the respiratory system. When things want to go from past a membrane, okay? If things want to go past a membrane, they got to be able to get through it. And that membrane is going to resist it. If you produce a surfactant, it makes it easier to go through. It lowers the energy, it lowers the surface tension. Here, I'm going to give you another example. You're probably not going to, many of you probably won't understand it. But if you spray an herbicide, okay, something that kills plants. And you just spray that chemical on there and the plant just goes, hey, bite me. How come? Because that chemical could not get inside the plant. Does that make sense? The chemical couldn't get inside the plant. So what you do is you mix up a surfactant with it, which kind of like pulls the cells so that pesticide, that herbicide can get inside. So when you look at Roundup, Roundup will say comes with surfactant. Now you know what a surfactant is. Okay, now let's look about it in your lungs. You breathe in oxygen, okay? Your blood wants the oxygen, but the oxygen doesn't want to come out of your lungs. It's saying, hey, I'm happy here, man. It says, no, 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 I want you to diffuse into the blood. It says, nope, the door's too small. So you stretch the door, making it easier to go in using a chemical compound called surfactant. And the oxygen then diffuses right through the wall, and waiting for it is hemoglobin on a blood molecule, red blood cell. Boom. You understand? Definition, you ready? Surfactant lowers surface tension. Corticosteroids. Boy, did I have a problem with these guys. Okay. Your adrenal gland that sits on top of your kidney has two layers, an outside layer and an inside layer. The outside is called the cortex. The inside layer is called the medulla. The medulla part produces adrenaline. Norepinephrine, epinephrine, those are adrenaline. That's produced by the medulla. The outside, the cortex, actually produces three major categories of steroids. They're called the corticosteroids. Glucocorticoids, what do you think? Glucose, yes. So when your body is going to go through mitosis, repair, you've had an injury, had surgery, you've been burned, okay, that's when it really flooded. It'll trigger the hormones, collectively called the glucocorticoids, to be released in the blood, and it will raise the glucose level in the blood. Okay, so I had to get a cortisone shot because I had a problem with my spinal cord. Okay, cortisone shot triggers the corticosteroids from the adrenal gland, the glucose release and raise the level of glucose in your blood because you're injured. Okay, so my A1C, which is supposed to be like 7, 6.5, is 10.6. And the doctor goes, oh my God, what's wrong with you? We need to come in and do tests. I said, I just got a shot of cortisone. Okay. And he said, well, yeah, but it shouldn't be that high. I said, the hell it isn't, man. My adrenal gland is doing exactly what it's supposed to do. I had to take the doctor back to school. Okay. You're thinking, well, what kind of doctor is that? He wasn't thinking of the injury. He wasn't thinking of cortisone being in there. So if you get a shot of cortisone, I guarantee your blood glucose level is going to go up because it's doing exactly what it's supposed to do. Okay. The mineral corticoids, the other corticoids, this is the one that takes care of sodium and chlorine and stuff like that. Okay. And the last one is the gonadocorticoids. That deals with release of production of testosterone, estrogen, and stuff like that. Okay. Okay. Now we did one. We did glucose. Whew. We did 2. We did fats. Whew. Now we're going to do nucleic acids. Okay. Nucleic acids are a pearl necklace, and the pearls are nucleotides. The function of nucleic acids is for storage of genetic information. The way your nucleic acids come apart, you put all of your nucleic acids in the nucleus of a cell, and any cell can make another one of you. Okay, that's called stem cells. The older we get in life, whether it's embryonic or post-embryonic, we start losing the ability for stem cells. We have very few stem cells left. One of the stem cells is for making cartilage. One of it's for making blood. We don't have too many more. Okay, they've become very specific, and they can't go back the other way. 2 classes of nucleic acids. Here we go. DNA, deoxyribonucleic acid, and RNA, ribonucleic acid. And I already showed you, this is a pentose sugar. This is a pentose sugar. Ribo, deoxyribo. You still see the nucleic acid. You see? So they're all built the same. There's two major classes. These are test questions. Both are polymers of nucleotides. Now you see the word polymer? You know what it is now, huh? It's a whole bunch of pearls. The pearls are nucleotides. Oh, dang it. I didn't want you to see that. Close your eyes. Close your eyes. Close your eyes. Close your eyes. Okay. Nucleotides. Well, what the hell is a nucleotide? A nucleotide is a smaller chemical compound. You see, if we took the pearl of a nucleic acid and smashed it, we could see what it was made out of, that pearl was made out of, and it's made out of nucleotides. Do you understand? Got it? Got it? It's made out of nucleotides. Okay? Well, what makes up a nucleotide? I got you, grasshopper. Okay? Nucleotides have three compounds. One, sugar, and it's either a pentose, we know it's a pentose, and it's either ribose or deoxyribose. There isn't a third type, okay? A phosphate, which contains the sugars, which connects the sugars. So you have here's what you have. You have a phosphate, and you have a sugar with a phosphate, okay? And the phosphate, I'm gonna draw it for you. Hang on. That pencil's jacked up. Okay, I'm gonna draw it for you. Here's a phosphate. I'm gonna draw it as a circle with a P in it. Here's the sugar. I'm gonna draw a sugar with, I'm just doing these two things right here. Okay, sugar and phosphate. Then I'll draw another phosphate, and I'll draw another sugar. See what I did? Okay, now that's the backbone. What we're missing is the third component. And there it is, nitrogen bases, and there are 5 of them in our body. And the nitrogen base comes off the sugar. And I'm going to put NB with a circle around it, NB with a circle around it. You see it? Okay, now NB can be one of 5 things. It could be, I'm going to show you. Let's go to the next one. I was going to write it. That's pretty stupid. There are 5 different types of nitrogen bases. Okay, this is the basis for protein synthesis, the way your body works, making cells and doing all that kind of stuff. These 5 fall into 2 groups, purines and pyrimidines. Purines are double rings, and there are 2 of them. Got it? Adenine and guanine. Adenine and guanine. So remember this NB thing I put? Remember the NB thing I put? We'll take the NB, which is these things, and we'll make it an A, a G, or it could be a pyrimidine, and those are single rings. There are 3 of them: cytosine, thymine, and uracil. So what I'm going to do to show you this, I'm going to take that NB, I'm going to put a line through it, means no, and I'm going to make it an A. I'll take the other one and I'll make it a C. See what I did? So what I did is I took a very generalized thing and I made it a little bit more complex. Do you see? Got it? So what I did is I said, okay, here's the 3 components: phosphate, sugar, nitrogen base. Phosphate, sugar, nitrogen base. And I picked the nitrogen base as adenine and cytosine. I could have made it guanine. I could have made it uracil, thymine. You get it? When you bond these things together, it's called complementary base pairing. So I'm going to flip this upside down. What I'm doing is I'm building you a DNA molecule, Jekko. Okay. Phosphate, sugar, phosphate, sugar, phosphate, sugar. See what I did? Got it? Okay. Now I'm going to make a complementary strand. Phosphate, sugar, phosphate, sugar, phosphate, sugar. You see the complementary strand? What's missing? What's missing? Come on, man. What is missing? The nitrogen base, the NB. But remember, we got more specific, and we made them ATGCU. Got it? But in DNA, there is no U. In DNA, it's always a T. In RNA, there's no T, it's a U. Only difference. So I'm going to make this DNA. So remember the sugar? I'm going to go one side, I'm going to go C, A, T. Oh, shit. You didn't hear that. Screwed that up. C, T, and we're going to make this an A. You see what I did? That is a mistake. Okay, see next to the sugar, I have a cytosine. Next to the sugar, I have a thymine. Next to the sugar, I have an adenine. So what will it bond with on this side? Remember? Okay, I'm going to show you this. It's called complementary bonding. An A will only bond with a T, or a T to an A. A G will always bond with a C, or a C to a G. In RNA, you just replace the T with a U, and it's the same bonding. So what I put down here, purines only to pyrimidine, specifically A to T or U, and G to C. So what should I put right there? If this is a C, nitrogen base C, what goes to C? Look down here. Come on, man. A G. Yes, you're right. So I put a G there. What goes next to a T? An A. Good job. What goes next to an A? A T. Good job. I just built your DNA for you, man. You see it? And then purines, A and G, G only goes to C, and they're double rings. So there's 3 bonds. A to T is 2 bonds. A to T is 2 bonds. You see the little dashes I put? See the little dashes I put? Real hard to see. That's how they bond. I'm going to show you all this in a minute. Are we good? That's called complementary base pairing, and you just did it. DNA, there's only 4 nitrogen bases, A, T, G, and C. This is a test question. In RNA, there's also 4 nitrogen bases. It's A, U, G, C. Got it? Okay. RNA, A, U, G, C. We good? I can go through this quick because this is just straightforward memorization. I'm going to ask you test questions on this. I'm a complementary base pairing. Now, we just did this. Here's your DNA strand. DNA is always a double helix. Look, this is parallel. This is a helix. Parallel, helix. DNA is a double helix. It means you have 2 sides to it. If we separate it out, it looks like this. Phosphate, sugar. Phosphate, sugar. Phosphate, sugar. You did this. Okay? And the same thing. Ooh, that was terrible. Excuse me. I got all worked up. Okay? Here's the same thing. Phosphate, sugar, phosphate, sugar, phosphate, sugar. So that we just picked a nitrogen base cytosine, guanine, thymine, guanine. So what bonds always with a C? A G. So there we go. 1, 2, 3. Those are hydrogen bonds. What bonds with a G? A C. 1, 2, 3. What bonds with a T? An A. 1, 2. What bonds with a G? A C. 1, 2, 3. And that's how we build our DNA. In your cell, every cell of your body, except for red blood cell, is built this exactly the same way. Okay? And when we have a series of these nitrogen bases on one side or the other, it's called a gene. And it has enough genetic code to make something. You getting it? And here's a whole bunch of them. See what they do is they just stop drawing this stuff. And they don't draw this, they just show it bonded together because we already know what it means. It's shorthand. A to T, G to C, T to A to T, G to C, T to A. You see what I mean? It's always the same. That's called complementary base pairing. That's why you never, ever make a mistake. Okay, now we're kind of heading into, I'm right on the verge. I'm on like slide 43. I'm like on slide 43. And so we're doing complementary base pairing. No, I'm not. I'm on slide like 38. Never mind. So this here and this here and this here are exactly the same thing. So this and this are the same thing. This and this are the same thing. So what this is, remember I said enough of these together would make a gene? So this is messenger RNA. We've heard this on TV, haven't we? Because we heard it on TV because we were talking about the vaccine. Okay, I kept thinking inoculation. The vaccine is a messenger RNA vaccine. So what we did is we built this thing ourselves in the lab, and we administering it into your body, into a sphere called a capsid, which is made of a protein. And then we made it so it would attach to the virus, and then you can kill the virus. Okay, so this is messenger RNA. You know how you can tell it's RNA? See the U, see the U, see the U. Do you see any T's? No. Do you see any T's here? Yep, there's one there, one there. So this got to be DNA. And you see the A bonds with the T. You see that? Okay, so this is messenger RNA. In order to do that, you take and unwind your double helix, and then you make a copy of the gene you want to go out to make proteins. These brown balls are amino acids. So I'm going to show you this when we do protein synthesis. But what we do is, this is a ribosome, which is an organelle. You have a large subunit, small subunit. These are codons. I'm going to explain all this stuff to you. You're going to make a protein. Don't freak out on me. I know you're going, oh, my brain won't wrap around that. Yes, it will. I promise you. I've done this semester after semester for a long time, like 2 days. And I've done it for a long time, so I can get this across. What the advantage you have now over being in the classroom, you can pause this and back it up. When we're in a classroom, I don't back up. Okay? Got it? So you're in good shape. All right, here we go. Okay, and I threw this ATP because we talk about ATP as the energy source in our body, right? It's a unique nitrogen base. Okay, here's adenosine. There's your triphosphate. Okay, 1, 2, 3. That's your triphosphate. 1, 2, 3, and it's attached to a pentose sugar ribose. Got it? And adenine is the nitrogen base. So we have adenine, triphosphate. Remember the sugar just is holding the nitrogen base in place. You get it? You get it? Okay. Differences between DNA and RNA. DNA, deoxyribonucleic acid. RNA, ribonucleic acid. It's just the sugar, baby. Just the sugar. Contains deoxyribose. Contains the nitrogen bases A, T, G, and C. We just did that, didn't we? Bases in DNA are A, T, G, and C. What are they? Go back to your notes. That's why you're taking these notes, to refresh your memory. Sure, am I going to tell you in about a blink of an eye? I sure am. But I want you to think about it. Okay? DNA is a double helix. I showed you that. All your genetic information is in DNA. Let's go back up to RNA. The sugar is ribose. What are the nitrogen bases? A, what? A what? UGC. AUGC. Just you switch out the U for a T, or a T for a U. It is a single, it's linear. If we took that double helix, remember that double helix? We took that double helix, took one of them, we have RNA, provided we put a U in place of T. 3 types: messenger RNA, which is how we made that vaccine. Messenger RNA, you always do a lowercase m, capital R, capital N, capital A. Ribosomal RNA and transfer RNA. Now, those probably mean nothing to you, but they're going to mean it here pretty darn quick. And tRNA and mRNA and RNA are the only types of RNA. So that would be a good test question, huh? Which is not a type of RNA. They carry the coded message from DNA. You can't tell DNA to go out inside the cytoplasm and say, start making this protein. And when you're done, come back. DNA will say, no, I like it out here. I ain't coming back. And that means that cell can no longer do what it needs to be doing. Does that make sense? Okay. So we make a copy of the gene we want and we send it out. And it goes through the holes in the nucleus called nuclear pores, and it goes to a ribosome. Remember that great thing I said, there's a big subunit, a large subunit, a small subunit, goes out there, and then it's being read. Okay, you make messenger RNA, you send it out to a ribosome, it's being read by ribosomal RNA, and it's bringing in a transport vehicle called a tRNA that's bringing in amino acid. There it is. I just gave you the whole protein synthesis. Got it? I will do protein synthesis. Now I want to talk about proteins. It's the 4th one. You can stop me at any time. Okay, just hit pause or come back to it. All right, proteins. Amino acids are the monomers. What were the monomers of carbohydrates? Think. What were the monomers? Think. What were the monomers? Think. The monomers were amino acids. Sorry, I screwed that one up. The monomers were monosaccharides. In proteins, they're amino acids. How many amino acids are there? You're going, hell, I don't know. I told you. I've told you in this lecture. How many of them are there in all living things? 20. Not 21. There's not 19. There's 20. Okay, and some of them are essential and some of them are non-essential. Okay, and I'll explain what that means in a minute. Monomers, and they're connected by a covalent bond called a peptide bond. Remember we said that 3 types of bonding: ionic, covalent, and polar or hydrogen bonding. Remember that? Okay, we don't worry about polar bonding. I gotta be careful which finger I leave up. Okay, we don't talk about polar bonding. I was gonna put this one down, but I ain't gonna do that. Okay, so, and it's not ionic bonding, which leaves covalent bonding. And when we're putting amino acids together, we give a special name to that covalent bonding, and that's called a peptide bond. Okay, and when we put 2 amino acids together, when we put 2 saccharides together, we call it a disaccharide. We put 3 saccharides together, we put a trisaccharide. Got it? When we put amino acids together, it should be called a diamino acid, but we don't call it a diamino acid, we call it a dipeptide. We put 3 of them together, we call it a polypeptide. You see? I think my computer's on fire. Ooh, something doesn't smell good. In all living things, there are 20 different amino acids. Do you see? 9 of them are essential, 11 are non-essential. Now, I've heard as much as 11 of them are essential. When I learned it, it was, my computer's going to jack up. I'm afraid we're going to have a fire. My house will burn down, and you guys will, and I'll start doing, oh, no, there we go. It's working. Glucocorticoids, remember that? Okay, anyway, get back to the point. When I learned that there was 9 essential ones, which means we have to eat them. Doesn't mean you have to have them. It means you have to eat them. That means you have to have plants or animals that have those 9 essential amino acids. They're up to between 10, or research is saying you got to have 10 and sometimes 11. So I won't ask the question. I used to say 9, but there's schools of thought out there that are saying 10 and 11. Whatever it is, it's got to add up to 20. So if there's 11 essential, there's only 9 non-essential. What non-essential means is they can be converted from the essential. Do you understand? They can be converted from the essential. That's what it means. Essential means you have to eat it. Non-essential means it can be converted from the essential ones. We can tweak them with enzymes. And this is a problem we have with people that are vegan or what else they call them? Plant eaters. That's how I learned it as a biologist. Anyway, people that don't eat meat, okay? I don't know how I can get by without eating meat. But anyway, don't eat meat, have to be very careful that they get the essential amino acids. So you're saying, well, I'm just going to have iceberg lettuce. You're going to die, okay? You have to have the beans and stuff like that. And that's still plant matter, but they contain the essential amino acids. Cereals contain the essential amino acids. That's why they make them that way, okay? If you eat a steak, you get all 20 of them. Got it? So if you go down and eat a hamburger, you eat a pork or chicken, you're going to get all 20 amino acids because they're found in proteins. They're the proteins found in the meat, the muscle functions. What are proteins used for? Catalysts. Okay, and I put in parentheses enzymes. Okay, you're going to say, well, what's the difference between an enzyme and a catalyst? Good question, Grasshopper. Now, Grasshopper comes from a movie called Kung Fu, had David Carradine in it. And when he was a young kid, his master called him Grasshopper. And he was always impatient. Master, why is this way? Patience, Grasshopper. Okay, so now you know where it comes from. I'll use that. It's kind of a little bit of humor. Catalyst. What's the difference between a catalyst and an enzyme? Patience, Grasshopper. Okay, a catalyst. Let's say you're mixing something on the stove. Let's say I always do this one. Let's say you're mixing Kool-Aid, and you pour in water, and you pour in the little packet, yes, of Kool-Aid, and you mix it up, and all of a sudden your Kool-Aid is red, right? What's the most popular flavor of Kool-Aid? Okay, now for those of you that said red is a color, okay? It's cherry. What's the second most common? Grape. What would and they cost the same amount of money. What would my mom get me when I was a kid? Orange. I said, Mom, can't we have cherry? Nope. Can I have grape? Nope. Orange. Why? Because. That's what I got, because. And if I asked again, I got whooped, okay? And then my mom would dilute it. So you look on the side of the package, it says it makes 2 quarts. Add a cup of sugar, or 2 cups of sugar, right? So you pour the sugar in, and the sugar goes, and it sits on the bottom. How do you get it into solution? You take a spoon or something and you stir it, right? Duh. Okay. What you are by stirring it is you are a catalyst. The catalyst is the stirring, and by doing that, it will lower the energy of activation. That's the definition. Lowers the energy of activation and cause it to become a solution. Remember we did solute, solvent? Okay. So when I got out on my own and I went to college, I mean, my mom made, when it got half, when the Kool-Aid got down to about half, she'd just add water, Jack. So what you were drinking is, let's say you had orange, it was just a little slight color of orange, and all you could taste was water, Stockton water. Nasty, okay? So when I got out on my own, I bought nothing but cherry Kool-Aid, and I bought pounds of sugar, and I'd put sugar in until I mixed it, and it wouldn't go into solution. So I had to add another catalyst. You know what it was. Some of you said, I don't know, tell me the answer. No, I want you to think about it. I used heat. Heat is a very common catalyst. So I'd put it on the stove and I'd heat it up and stir it, and it would go into solution. I'd pour it in there. And let me tell you something. When I made my Kool-Aid, you were buzzing on sugar, okay? Which I needed a lot of time for studying. Enzyme. Now you know what a catalyst is. Lowers the energy of activation. I gave you an example. Physical moving, heat, that kind of stuff, okay? Shaking, all those things work. Once you take a catalyst and put it in a living organism, it is now called an enzyme. So an enzyme, by definition, is a catalyst in a living organism. Did you get that definition? You're going to see it on the exam. We also have proteins as antibodies. You've been hearing a lot about that, making your own antibodies. We have certain white blood cells that identify things in your body that aren't supposed to be there. because they're always looking. They're trying to find, oh, that's not supposed to be there. So what they do is they measure it up and they go to your DNA code and they say, make an antibody to surround this thing or kill this thing. Okay, and that's what they're doing with this vaccine that we're doing. When we inoculate you, we are inoculating you with essentially a dead, when we do the flu vaccine, let's get away from the COVID. They take the protein and they heat it up, and inside of it is nucleic acid, and they kill that nucleic acid. So they give you an empty capsule, and then it allows your body to see that, produce the antibodies. So when you do get it, it has a little army out there to go out and whoop its butt. You understand? Antibodies are proteins, structural and support proteins, tendons, ligaments, fingernails, hair. I always go like this with hair, and then I realize, oops, hair. Okay? Those are all proteins. Those are called structural proteins. And then transport proteins. Huge when we start talking about the cell. When we talk about the cell, we have to get things into and out of the cell. Okay? And that requires a transport, usually a transport protein, usually. And those are called integrated proteins. They're like a channel, like a big doorway. Okay. If you want to move stuff in the blood that is non-protein, like a lipid is hydrophobic. You have to attach it to a protein. Those are called transport proteins. Storage. Okay, we have proteins used for storage. Okay, amino acid, primary structure. Now, proteins have 3 or 4 structures. All of them have to have 3. Some have 4. Okay. Okay, here they go. Number 1 structure is the linear sequence. It's called the primary structure, and it's connected by peptide bonds. That's what we do in protein synthesis. Here's your amino, and there should be a C here for acid. Amino acid. Amine group and a carboxylic acid. This should be a C double bond O, which is the carboxylic acid. This is the amine group. The N, nitrogen, makes it an amine group. This is an amino acid. Understand? I think I have it right. There we go. There we go. C double bond O. That's incorrect. This does not go there. That can't be, because that would have a bonding capacity of 3. That's not it. Okay. So this goes up to there. Got it? So this is a generalized structure of an amino acid. Amine acid. In between, the reason I didn't put it, it's in between here, we put different things in, and there's 20 of them. 20 different things we put in between, and that gives us the different amino acids. You understand? Okay. Proteins have 3 or 4 structures. First one's primary. Primary is the amino acid sequence. What amino acid's next to which amino acid connected by a peptide bond? Secondary. Okay. So when you have here is a linear sequence. The wire I'm showing you is a bunch of amino acids hooked together. Pearl necklace. Got it? The pearl necklace. Okay. Now, that's primary. Secondary, because you have hydrogens out here, okay? You have hydrogens out here, they will bond, and they start doing this. And they start forming a helix. Do you see it? See the helix? Okay. So when you form the helix, that is called its secondary structure, and it's based on the hydrogens that are hanging out there. So it's based, here's what I put. Secondary is called an alpha helix, alpha because it's not beta, there's only one string, or pleated sheet determined by the H hydrogen bonding. Got it? Test question. Tertiary, this is the 3-dimensional shape determined by hydrogen. So not only we have this going on, but it bends back on itself. And that's 3-dimensional. So the 3-dimensional shape determined by hydrogen bonding, covalent bonding, and disulfide bridges. I'm going to show you a picture of it. But you see, primary, secondary, tertiary, tertiary. Okay, one more time. Primary, secondary, tertiary. Get it? Yeah, I'm giving you a hell of a lot of information. I get it. Okay, and we're on the downslope side. Is this what you're going to have to study? Absolutely. Now, quaternary, not all proteins have quaternary. Quaternary, by definition, means you have two or more chains. Quaternary is not present in all functional proteins. Some proteins need two or more polypeptide chains bonded together in order to be functional. Example, hemoglobin. This is one. If I had, just pretend like it's different. If I had two of them bound together like that, this would be quaternary structure. And I could have two, or I could have four. An example of a four chain hooked together is hemoglobin. It's found in the red blood cell. Got it? Got it? So hemoglobin happens to have quaternary structure. Okay? Insulin does not. Okay? All right. Primary, no. Primary, see it? Carbon, carbon, nitrogen, carbon, 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 C double bond O, see the C bond O. This is the acid. This is the nitrogen. This is, and this R, remember, there's 20 different R's out there. So this is primary. Amino acid number one, amino acid number one, amino acid number two, amino acid number three, primary structure, polypeptide strand. This is how when we make a protein, this is what we make. And then because you have these hydrogens out here, it zips into an alpha helix, a single stranded helix. Got it? And then it winds, that secondary structure, then it winds back on itself like that, like a ball, like I showed you, and that's tertiary. And then it may or may not require two or more. So this would be 1, 2, 3, 4. So this would be hemoglobin. See how they put it down here? Because there's 4 of them. Pretty good? Okay. How do enzymes work? You have an active site. In lab, it's pretty cool because I can come out and what I do is I take one student, I put my hand on their shoulder. I take the other student, I put the hand on the shoulder, and I can pull them together. That's what an enzyme does. But the enzyme has to have the shape that is required to fit on that shoulder. So when we have a substrate, that's a shoulder. We have another substrate. The enzyme has to be able to identify both of them. If it doesn't have the three-dimensional structure, remember three-dimensional structure? It can't work. So you have to have an active site. Active site, this is the three-dimensional shape, can be altered by pH or temperature. This is a test question. How can you denature? Denature means to change the shape of a protein. There's 2 ways. And there it is. pH and temperature. Okay? I'll just give you an example. I had a buddy, it's a long time ago, and he was a potato farmer out on King Island, out in Stockton. And it was one of those days that was just blistering hot, 111, 112, 113. And he was going down and in his truck and he was checking the checks. Check is where it's depressed and water runs down the check and that feeds the roots of the potato plant. And he's going down and wherever there wasn't water going in, he'd jump out of his truck and he would make the water come out of the main ditch going into the check. You understand? So he's out there doing this on hundreds of acres and it's getting hotter and hotter and he stops sweating. Didn't realize it. He's getting in the car with the air conditioner going. He doesn't realize it. And when he comes back into the prep area where he has all his machinery and stuff, he steps out of the car and drops dead right there. What did he die of? You want to say died of temperature. No, he didn't. What happened was the temperature changed the three-dimensional structure of the enzymes that were required for metabolism, to keep him alive, to keep the heart beating, to keep respiration, to keep his brain going, okay? And it changed it to where it shut down all the enzymes. He had no more energy. He had no more, heart stopped, blew out his heart, blew out his lungs, blew out his brain, okay? Okay, now, you're thinking, how could an intelligent person even get the intelligence of the person do that? Yours truly 3 years ago did exactly the same thing, only I didn't die. We had company coming over. I went out to mow the lawn, and I got a big lawn here. So I'm on a riding lawnmower, and it's hotter than hell. Okay. I know what it feels like in hell because I was there. And I'm mowing the lawn, and the company's getting close. I'm watching my watch, and they're going to be coming down the street. So I'm going. And I ran out of water. I was so dry. I could feel my skin was dry, and I went, I'm having a heat stroke if I don't hurry up. So by the time I got off my stupid ass and went in the refrigerator, the first thing I opened it up, I saw choice, Pepsi, water. Guess which one I picked? Pepsi. Not a good choice. So I pounded 12 ounces of Pepsi. Did absolutely no good. Then I pounded another Pepsi. Did no good. And this is in seconds. Okay. Pretty soon my head's all screwed up. I can't talk. I'm slurring my speech. Feels like I'm drunk, and it sounds like I'm drunk. Well, my honey was gone. So man, I crawl into bed and I'm shaking like I got the chills and I can't do it. My daughter calls. She starts talking to me. She goes, Dad, have you been drinking? I said, honey, you know I don't drink. She goes, well, you're screwed up. I'm going to call Sandra and have her come home. I couldn't even speak to her. I couldn't hold the phone. So it's leaning against her. I'm on against a pillow. And she comes home and she takes me down to go to the bathroom, and it's a mess. I'm bouncing off the walls. Okay, see what happened? If I would have been on that lawnmower another 10 minutes, you wouldn't be looking at me right now. Okay. It took me almost 3 days, and I still, 3 years later, still have problems with it because part of my brain fried, just like it would be with another stroke. You know, you lose blood to your brain, your cells die. Well, I lost blood to my brain because of the heat. And it's serious. Okay. So temperature denatures the protein so they can't do their job. If I died, I would have not died from heat. I'd have died from the lack of the ability of the enzymes to do their job. And you can do the same thing with pH. You start playing with the pH, that's what's going to happen. Okay, nice little story. Enzyme substrate complex. Okay, how do enzymes work? Remember the hand goes on the shoulder, enzyme on the enzyme. Hand goes on the shoulder, shoulder's the substrate. Shoulder's the substrate. I can bring the two shoulders together and form a new compound. You understand? That's called enzyme substrate complex. I bring them in. Do you understand? It is a generalized term. Now we know we have to have specific enzymes, right? Specific enzymes. Okay, got it? So we take it one step further in another definition. It's called the lock and key theory. Can you open up any lock with any key? The answer is obviously not. How do you open the lock? Well, I have to have a specific key. Okay, so the key is the enzyme. The lock is the substrate. So it's specific. So if you want to break down lactose, which is milk sugar, what's the enzyme? What's the key? Lactase. You want to break down maltose, what is the key? Maltase. ASE makes it an enzyme. You get it? It's specific. So this one is generalized. This one is specific. Are you with me? Moving on. Naming, substrate plus ASE. The old form, one of the first enzymes that were isolated was pepsin in the stomach, because they wanted to know, how are we breaking this stuff down? I'm eating a pearl necklace and all of a sudden it's being absorbed. How come? So we started isolating the enzymes, and we started with pepsin, secretin, gastrin. So we started playing where they come from, and we added an IN. Well, then we realized there's tons of enzymes. So we had to name them a special way. We kept the original ones with an IN. All the other ones was the substrate with an ASE on it. So if I want to get down my got it? Remember the helix of the DNA molecule? Okay. How do I break down the helix? Helicase. How do I break down? Got it? Got it? Okay. So they got to be specific. Okay. I hope you got it. Here's my hand. Here's my other hand. Here's the shoulder. Here's here's the shoulder. Because of my three-dimensional structure, I can bring those together. And in this case, you only got part of it. You see, only part of it. Substrate made a new product. And then the enzyme is unaffected. And go back and do it again. This is a protein. Do you understand? Okay. So it takes an enzyme to bring two substrates together or to break them apart. If you make the arrows go the other way, you're breaking them apart. It requires an enzyme. And that enzyme's got to be specific. So it's called the lock and key theory. But to be specific, it's lock and key. And this is just showing you an arrow. Okay. We're done. I know that was long. Okay, I'll attach this to organic chemistry, biochemistry. The next thing we will, so the next one that I'm going to record for you is protein synthesis. It won't be as long, but you'll at least know something about it. Messenger RNA, ribosomal RNA, transfer RNA, yada, yada, yada. Okay? Okay, thanks for bearing with me. It was long, but you don't have to listen to the whole thing at once. You can shorten it and listen to it again, okay?